Hey everyone, it's Dr. Walker. Let's go over the second example from v035C on non-uniform circular motion. This example, we have a ball attached to a string of length L and swung in a vertical circle about a fixed point. Find the tension in the cord at any instant when the speed of the ball is v and the cord makes an angle theta with the vertical. So let's picture what's going on here. We have a ball swung in a vertical circle about a fixed point. Let's say this is the fixed point. And it's going to be swung in a vertical circle. And we're saying, what is the tension when it makes an angle theta with the vertical? So we can find the tension anywhere along the path, but let's find the tension when, instead of being at the top of the path or at the bottom of the path, let's say that the ball is over here. It's making an angle theta with the vertical. And let's say that it's going clockwise, so here it has v, velocity v, and so here it has velocity v. All right, let's find the tension at that point. So the first thing to realize is this is non-uniform circular motion. We'll talk about why in just a second, but we can still solve this problem the same way that we solved the uniform circular motion problems. Because if we're looking for tension, we know that tension is pointing towards the center of the circle, right? Tension always points away from the object. I'm actually going to draw a separate free body diagram down here. So let's look at this ball here. And so it has tension pointing away from the object. So if we look at the centripetal forces, we can still find tension, even though there are forces that are tangential to the motion as well. For instance, if we look at the weight here points straight down, but it has a component that is tangent to this circle, right? That is parallel to the path. And there's a component that is perpendicular to the path. So we can still just look at the centripetal forces pointing towards or away from the center of the circle. This component of the weight here points away from the circle. So we just need to figure out what our theta is. If our theta was over here, then this theta happens to be the same as this theta over here. And you can see that, maybe you can see it more easily if you look over here. Because if you have a straight line here, right, you know that these two thetas here are corresponding angles. And then, so if you make another triangle over here, now you can see that these are the alternate interior angles. All right, so that being said, let's look at the centripetal forces. Centripetal forces equal mv squared over r. Towards the center is tension. Away from the center is this component right here, which is adjacent to the angle. So if the hypotenuse is w over here, that means that this is w cosine theta, which is mg cosine theta. So t minus mg cosine theta equals mv squared over r. We're trying to solve for tension, so tension is equal to mv squared over r plus mg cosine theta. We don't have any values, so this is the answer, but let's take a look at a few important things to note. This problem is very similar to the example that we did earlier with the roller coaster. You can be over here, which corresponds to being upside down in a roller coaster. If you remember when you were upside down in a roller coaster, you had a normal force and a weight pointing straight down. Well now, if you're here, you just have the tension and the weight pointing straight down. Right, so very similar. If you're at the bottom of the roller coaster, it's like this case right here where you have the tension instead of a normal force and the weight going straight down. The equations that we derive for the roller coaster, we can derive them for right here as well. For instance, if we are at the bottom, let's put it here, right? If we're at the bottom of the path here, then the angle is 0. Cosine of 0 is 1. So we would get tension equals mv squared over r plus mg, which makes sense because if we were to set up the equation up here, it would be T minus mg equals mv squared over r. So the last thing that I want to say about this example is the reason it is non-uniform circular motion, right, is because of this tangential component of the weight, this w sine theta over here. It causes the ball to speed up and slow down. If it's going clockwise here, then it's an acceleration that's opposite the motion, so it causes the ball to slow down as it's going up. But as the ball is coming back down, it causes it to speed up. So even if we have non-uniform circular motion, we can still look at the centripetal forces and the tangential forces separately, and sometimes only looking at the centripetal forces is enough to get us to what we're looking for.